Hello everyone! In this video we are going to look at three shapes of graphs of cubic functions, and we will talk about differentiation a little bit to explain something. Now let's get started. We remember the equations of the following graphs. The main shape is climbing up double hills. The equations of these graphs will be the factorized form because the main trend is climbing up. The coefficient of x cubed is positive, and then based on the number of x-intercepts, the first graph, the equation will be a times x minus alpha times x minus beta times x minus gamma. Here a is greater than 0. And then for the second graph, there are two x-intercepts. The graph cuts the x-intercept at x equals beta and touches x-axis at x equals alpha. Then the equation can be expressed in this way: y equals a times x minus beta and then x minus alpha all squared, because when the graph touches x-axis at this point, and we will have a repeated factor x minus alpha. For the third graph, it has only one x-intercept, and then in this case the function will be in this form. We will have the term x minus alpha, and then the second term we will have ax squared plus bx plus c, and then here a is still positive, and the discriminant of the quadratic factor will be less than 0. Now there is a question. From the graph we can determine the equations. What about if we have the function in the form of number 3? Does it mean we will always obtain the graph in the shape of climbing up double hills? Now let's look at these two functions. They both have a linear term, which is x minus 1, and then they have a different quadratic term. And then we are going to check. For this one, the a value is number 1, b value is 4, and c is 5. The discriminant is b squared minus 4ac. Then we will have 16 minus 20, which is less than 0. For the second function, the quadratic factor, similarly, the discriminant is less than 0. That means the graph of the cubic function will be climbing up double hills. Let's use technology to sketch these two graphs. For the first one, yes, this part climbing up and this part climbing up as well. That's why I call it climbing up double hills. X-intercept is 1. There is only one x-intercept. Now for the second function, we can see the graph is different. It is not climbing up double hills. It seems that it is just climbing up one hill, and the x-intercept is 1, only one x-intercept. Now the question is, why their shapes are different? Then we have to investigate how many basic shapes of the graphs of cubic functions. Now we are going to look at these functions together. We have already obtained the graphs of number 1 and number 3 functions. So we focus on the second function. Here it is a special case of the transformational form. By comparing with the transformational form, we can see value of a is number 1 and h is 1, k is 0. It means the graph of the middle function is like this. It is climbing up a hill, and there is a point of inflection which is hk. But for this function 1, 0, because h is 1, k is 0. Now we are going to look at these three graphs together to analyze their key features. For the first one, the shape is climb up double hills, and there are two turning points. You can see here one turning point, another turning point. These 2 points, they are flat. Now for the second graph, we know there is a flat point as well, and this point is called a point of inflection and not a turning point, because to the left of number 1, it goes up, the graph goes up. Now after the value of x equals 1, the graph continues climbing up. And then for number 3, the basic shape is climb up a hill, but here we can see there is no point of inflection. Therefore, the key features are different in terms of the flat point. And then we can also check the x-intercept and y-intercept of these 3 functions. For y-intercept, we can just let x be 0. And then for the first one, we will have y equal -5. For the second one, y is -1. And for the third one, y equals -2. And then for x-intercepts, we can see all of them have only one x-intercept. They all cross the x-axis at x equals 0. So this is the similarity between them. Based on these functions, we can see there are 3 basic shapes of the cubic functions when a is greater than 0. Now the problem is how we can explain the main difference between them. Here, we are going to look at the derivative of the function, but you may haven't learned differentiations. So this one, just try to get the basic idea, and you can revisit this part after you have learned differentiation. Okay, then we do in this way. So for these 3 functions, I am going to convert them to the general form of the cubic function. It means we are going to show the leading term x cubed, and then other terms in the descending order of the index of x. And based on this, we can use differentiation to get the derivative. And for each of them, the derivative is a quadratic function. It means the index of the leading term is number 2. Now we are going to focus on these different quadratic functions and try to calculate the discriminant. For the first one, the discriminant is greater than 0. It tells us for the quadratic function there are 2 real solutions. It means there will be 2 flat points. And then for the second function, the derivative is also a quadratic function. The corresponding discriminant is equal to 0. That's why for the original cubic function, there is 1 flat point. So at this point, we only have 1. For the third one, the corresponding derivative with the discriminant less than 0. That's why there is no flat point. So the main reason we can find based on the derivative. But at this stage, you just remember that there are 3 different shapes, and the number of flat points will be different. Now let's look at example 1. There are 2 functions involved here. Both of them are in their factorized form. For the first function, it has a linear factor which is x minus 1, and the quadratic factor. This part we have x squared plus 1, which is always positive, and then the sign of y will be mainly determined by the linear factor. Therefore, we can use the sign diagram to determine the shape. So the x-intercept is 1. To the right of 1, all the y values are positive because the linear factor is positive, and then to the left it's negative. Also, as we haven't learned differentiation at this stage, we are going to use the hint provided by the question. There is no turning point or flat point of this cubic. It means the basic graph will be our shape 3. It is climbing up a hill but no turning point, no point of inflection. It means no flat point. Then we will calculate the x-intercept by letting y be 0, and then here we can get x equals 1 directly, and then for y-intercept, let x equal to 0, we will have y equals -1. Then we are going to show the information on the diagram. X-intercept is 1, y-intercept is -1. But in order to make the graph a little bit more accurate, we are going to select some points. For example, I use the point with x be 0 and y is 5. And then another point, if x is -1, y is -4. I'm going to connecting all those points using smooth curve. Now the graph is like this, and we can see it shows consistent information with the sign diagram. For part B, it has the linear factor, which is x minus 1, and the question tells us there are 2 turning points. It means the basic graph will be climbing up double hills, and 2 turning points are here. And then we can determine sign diagram first, because the quadratic factor is always positive here. Then the sign of y will be mainly determined by x minus 4. So we label the value of x on the x-axis, and to the right of 4, all the values are positive. To the left of 4, it's negative. Then similarly, we are going to calculate the x-intercept, which is x equals 4 directly. Then for y-intercept, let x be 0, we will have y equals -8. Put all the key features on the diagram, then we will have the x-intercept and y-intercept. Then similarly, we will need some more points to make the graph more accurate. Here I used the points with x equal 1 and y -9, which is here. And then if I let x equals -1, y is -15. The point is here. I'm going to connect these points by a smooth curve showing double hills. Okay, the graph is like this. We can see there are 2 turning points. The exact coordinates can be determined by using the graphing calculator or use differentiation in the future. That's all for today's content. Thank you very much for watching. I will see you next time. Bye.